Hi guys, welcome to my YouTube channel, Love Learning and Thinking. This is me, Ryzen Fox Omega, and to very brief about me, I am an avid learner. I like learning new things, especially maths. Why maths? Because I feel maths is a mother of science. It has given birth to science, physics, astronomy, and it is a language that helps us understand the nature around us. So let's not waste time and dive into a very interesting concept in modulo arithmetic, that is the Euclidean algorithm. So what's the Euclidean algorithm? Euclidean algorithm, a timeless theorem. The Euclidean algorithm represents one of humanity's oldest and most elegant computational method, dating back to Euclid's Elements. This algorithm provides an efficient method for computing the greatest common divisor of two integers, a fundamental operation in number theory, cryptography, and computer science. The brilliance of this algorithm lies in its recursive nature. We given two integers a and b, where a is greater than b, the GCD of a and b equals the GCD of b and a modulo b. I will tell you what is a modulo b later in this video. This process continues until the remainder becomes 0, at which point the last non-zero remainder is GCD. This is just a mathematical formulation, you can skip it, guys. So guys, friends, let's dive into third slide, visualizing the algorithm. Initialization. Start with two positive integers a and b. Let's say 12 and 24. Now the second step, compute r is equal to a divided by modulo b, and notice the remainder when a is divided by b. A modulo b is nothing but checking the dividing a by b, that is 24 divided by 12. Here remainder is 0. If remainder is 0, then b is the GCD, that is the smaller of the two number is a GCD. Here out of 24 and 12, 12 is a GCD, and we terminate the process. But if the remainder we get after the division step is not 0, we continue this until we get the remainder 0. That is a recursive call. Repeat the process with b and air as a new pair. I know you might not feel very comfortable with this oral teaching method. Let's then take an example. Here I have taken a small two numbers 48 and 18. So 48 is 2 times 18 plus 12, 36 plus 12. So but the remainder we get here is 12, and as I told in the division step, check the remainder. 12 is the remainder, but remainder is not equal to 0. So we again have to repeat this method. 18 is equal to 1 times of 12 plus 6. Again 6 is not equal to 0. So we again repeat the procedure. Take 12 here, put it over this here, and then divide 12 by 6. Here we finally get the remainder is equal to 0. Therefore, if remainder is 0, then b is the GCD. That is here 6 is the GCD. Here this is the b. Okay, so therefore the GCD of 48 and 18 is equal to 6. Now my friends, you might be thinking that, oh Ryzen Fox, this was a very easy example. So for you guys, I have, and all the math enthusiasts, I have got a very nice problem. This is an Olympiad level problem. Let's see if you can find out its solution. This is a problem of the day, or rather problem of this video. This is an Olympiad level challenge. Let f of n denote the number of steps required by the Euclidean algorithm to compute the GCD of n thousand. Determine the maximum value of f of n between 1 and 1000 and find all n for which this maximum is achieved. That is, my friends, This question is trying to tell that we have to take two numbers between 1 and 1000 and try finding out the GCD. Then we have to, while calculating the GCD using the Euclidean algorithm, we need to notice the number of steps we are taking. And between 1 and 1000, there is a certain number for this is maximum. There might be more than one. It's all upon uh, how your thought process goes on. So I have also added some hints for approach. If you any of you guys know already this theorem, this might be very useful. So you can I will create a video on Fibonacci and Lemmy's theorem also. But for now, just think, and let me also think, because I have also not tried out this problem. I will let you know tomorrow if whether I was successful in finding out this solution or not. Now let us talk about some modern applications of the Euclidean algorithm. Why we are talking about the Euclidean algorithm? Because it is used in very important technological tools in our everyday lives, like cryptography and security, machine learning, very important, algorithm design, computer architecture. All of these areas require the Euclidean algorithm. They are based on the Euclidean algorithm. Like the HTTPS encryption. This is a real world application where GCD is required for key generation. So you need to realize that this algorithm is very lovely algorithm. It has got many applications. So if you just give a little thought, you might be able to solve further problems related to this, and we can get some more application based on the Euclidean algorithm. This is a computational complexity analysis. You can leave this slide. Just the some of the histories and how well this algorithm is good. The Euclidean algorithm exemplifies the timeless nature of mathematical insight. What began as a geometric proposition in ancient Greece now secures trillions of dollars in daily financial transactions and enables the artificial intelligence revolution. The journey for classical mathematics to modern AI demonstrates a fundamental truth. Deep understanding of theoretical foundations empowers innovations. The algorithm's recursive nature, elegant proof, and unexpected applications reveal the interconnectedness of mathematical disciplines. So, guys, that's all for today. Meet you in the next video. Till then, if you liked my video, please do comment and subscribe which theorem or which AI puzzle or proof you want next.